Hey guys, this is Professor Janacek, and I want to talk about finding the area of a region when we're looking in polar coordinates. First off, remember that the area of a sector, back from trigonometry or pre-calculus, is A is equal to 1/2 r squared theta. Now in this case, we're actually going to be looking at two different theta values. So we're going from alpha to beta just within that interval. So we'll write this as A is equal to 1/2 r squared delta theta. So what's the difference of those two theta values? All right, now r we'll define as a function of theta. And so we can then write this as A is equal to 1/2 f of theta quantity squared delta theta. Now, to introduce some calculus here, if we want to find the area under a curve, now this is under a single curve, then we'll introduce, of course, the idea of the limit of the Riemann sum, and that would tell us that the area then would be the integral from alpha to beta, so over that change in our theta values of 1/2 f of theta squared d theta. So that delta theta, the limit of that delta theta becomes d theta. Now, what we're really looking to get at, though, is the area bounded by two different functions f and g. So we'd already introduced the two different angles, alpha and beta, but now we're going to look at two different functions, f and g, and we want the area between those two. Notice that we are going to name the larger function f and the smaller function g. So when we do this, our area now becomes, as you would expect, the integral from alpha to beta of 1/2 times the difference of those two radius values. So that's going to be the larger one, f of theta. That's got to be squared, though, minus g of theta, which is also squared. And then we still have the d theta there on the back. So there we go. This is kind of what we'll be using to find the area between two curves in polar coordinates. Now there's a lot of kind of calculus that goes on kind of in between these steps, but that's all stuff that we've taught, that you should have seen before, that we've talked about before. Let's dive right in and take a look at an example now. Let's determine the area inside r equal to 3 plus 2 sine theta and outside r equal to 2. Now I've already taken the time to graph these. Notice that r is the cardioid. R equal to 3 plus 2 sine theta is that cardioid, and that's graphed here in blue. And then r equal to 2, that is a circle. That's graphed here in green. I will begin by letting f of theta equal to the cardioid, 3 plus 2 sine theta, and g of theta, the smaller one, be that circle 2. All right, now what we'll want to do is find the points of intersection, and I have those kind of highlighted here and here. That's going to give us our limits of integration. So the points of intersection. We'll find these just like you would expect. We'll set those two functions equal to each other. 3 plus 2 sine theta is equal to 2. Now, if you solve this, subtract 3 from each side of the equation, divide each side by 2, or multiply by 1/2, we end up with the sine of theta is equal to negative 1/2. Now, if the sine of theta is equal to negative 1/2, what is our theta value? Well, the reference angle is pi over 6, and so in quadrant 3, theta is 7 pi over 6. That's this one. And in quadrant 4, theta is, well, that would be 11 pi over 6. However, I want to make note that I can also write that as negative pi over 6. Let me explain why I've decided to write both of those angles here. So notice that we are going to go, our coordinate system goes in the counterclockwise direction. So I want to go from quadrant 4 to quadrant 3. In order to do that means I'm, again, from quadrant 4 to quadrant 3. And remember, when we integrate, here in a second we'll get to this integration, this has to be the smaller value and this has to be the larger value. So my limits of integration have to be in a particular order or things get a little messed up. So to ensure that I'm going in the proper order, I'm going to use the negative pi over 6 and not the 11 pi over 6. Again, make sure you understand I am going from quadrant 4 to quadrant 3. We are not going from quadrant 3 to quadrant 4. That would be this little bit here. Right? So notice that I want to make sure I'm going in the right order. If I'm going from quadrant 3 to quadrant 4, notice I don't have anything inside the cardioid but outside the circle. This little bit here is actually outside the cardioid but inside the circle. Okay, so we are going to integrate from negative pi over 6 to 7 pi over 6. And now we're going to just simply use our little area formula up there. 1/2 times, whoa, what happened there, guys? Oh. Get us back on track. Okay, there we go. All right, so we are going to take 1/2 times the larger function, that's 3 plus 2 sine theta, quantity squared, minus the smaller function, g function, that's 2 squared. And then, of course, we've got our differential d theta there in the back. Okay, so now, to get through all this, we're going to have to clean this up just a little bit. This bit right here, we can write this out as a binomial squared. So this is 3 plus 2 sine theta times 3 plus 2 sine theta. Take your time, multiply all that out, multiply, combine like terms, and see what you get. Also, notice we're going to also subtract that negative 2 squared, so make sure you do that. So multiply all this together, do that subtraction, combine your like terms, take a moment to do that if you'd like. You should end up with the integral from negative pi over 6 to 7 pi over 6 of 1/2 times, again, this is after all the things have been combined, you'll get 5 plus 12 sine theta plus 4 sine squared theta, d theta. Okay, pause it if you need, make sure you come up with all that. Okay, now, we're almost ready to integrate. I can definitely integrate 5, no problem. By the way, this 1/2 we can factor out at any time if we need it. But I can definitely integrate 5. I can definitely integrate 12 sine theta. I mean, again, 12 is just a coefficient. Sine of theta, we can integrate that. But this 4 sine squared theta, integrating that is going to be a bit of a problem. 4, I'm not so worried about. Sine squared, definitely worried about. We cannot integrate that. So I'm going to use one of my half angle identities. Remember that sine squared theta is 1 minus cosine of 2 theta over 2. So if we use that in here, we have 4 times 1 minus cosine 2 theta over 2 d theta. But now let's go ahead and reduce the 4 with the 2. So this gives us There in the back, all this front stuff is the same. There in the back we have 2 times 1 minus cosine. Actually, you know what? Let me go ahead. We could do this all together. I'll reduce that and go ahead and distribute that too, so we get plus 2 minus 2 cosine 2 theta d theta. Which means we can go ahead and combine that 5 and the 2. So we have one more time. Let's write it out, and then we'll take the integral on the next step. 1/2 times 7 plus 12 sine theta minus 2 cosine 2 theta d theta. Okay, so now integrating this, I think should be pretty straightforward. Integrate, okay, factor out that 1/2. If I integrate 7, I get 7 theta. Integrate 12 sine theta, that's plus 12, oh, wait, not plus, that's going to be minus 12 cosine theta. Now here we will have to use a little u substitution. If we let u equal to 2 theta, then du is 2 d theta. And so this 2 here in the front, I'm going to move to the back. And then I think that's ready to integrate. We will be integrating, let's see, so the integral of cosine 2 theta 2 d theta is the integral of cosine u du, which is the sine of u, which would give us the sine of 2 theta. Of course, don't forget there's a negative in front of all of this, so we keep that negative there in the front. Oh, so that gives us minus sine of 2 theta. And then we're going to evaluate this from negative pi over 6 to 7 pi over 6. Now, evaluating it, you should be pretty good at that. I'm going to go ahead and let you guys take care of that. See what you get. You should end up with 11 square root of 3 over 2 plus 14 pi over 3 when it's all said and done. Again, simply evaluate at 7 pi over 6 and then evaluate at negative pi over 6 and should be pretty good to go. Right. Not so bad. Enjoy.